Hey everyone, and welcome. Today we are diving deep into something that makes the entire internet work, the IP address. Specifically, we're going to unpack IPv4, the classic, original system that's been the backbone of our digital world for, well, a very long time. Let's get into it.
So think about it for a second. You've got billions of devices out there, phones, computers, servers, you name it. Every time you send a message or watch a video, your little device has to connect to another one, maybe halfway across the world. How in the world do they find each other in that giant digital haystack?
Well, the answer is the IP address. You can think of it as a digital street address for every single thing connected to the internet. It's a one-of-a-kind ID that lets all those devices on a network, what we call a TCP/IP network, find each other and actually have a conversation. It's the absolute foundation for pretty much everything we do online.
But what is an IP address, really? I mean, what are we looking at when we see those numbers? To get that, we've got to pop the hood and take a look at how it's built. Trust me, it's way more than just a random jumble of digits.
Let's start with an address that might actually look pretty familiar, especially if you've ever poked around in your home's Wi-Fi settings. 192.168.1.0. This is going to be our guinea pig for the next few minutes.
Okay, first thing you notice, it's not one giant number. It's 4 separate numbers, with a dot in between each one. And in the networking world, each of these number chunks has a special name, an octet.
So what's an octet? Well, it's just a fancy way of saying it's an 8-bit number. And because it's made of 8 bits, the math works out so that the smallest number it can be is 0, and the absolute biggest is 255. This is the golden rule. It's why you will never, ever see a number like 300 in an IP address. It's just not possible.
But here's the real secret, the part that computers care about. That dotted decimal format, that's just for us humans to read easily. Computers see the world in binary, just ones and zeros. So each of those octets is really an 8-digit binary code. You do the math, 4 octets, 8 bits each, that gives us a grand total of 32 bits for every single IPv4 address.
So what does the 32-bit system actually buy you? It gets you this many possible addresses, just under 4.3 billion. Now, when the internet's architects first came up with this, that number seemed impossibly huge. I mean, more than enough for every computer they could ever imagine connecting. As we're about to see, though, that assumption didn't quite hold up.
So picture this, you're one of the early internet pioneers, and you've got this pool of over 4 billion addresses. That's potential chaos. How do you start to organize it? Well, the first solution they came up with was a system of classes. They basically took that entire 4.3 billion address pie and sliced it up into 5 main categories, which they creatively named A, B, C, D, and E. And as you can see, these slices were definitely not all the same size. Class A, for example, took up a whopping half of the entire address space.
Now, the 3 main classes you really need to know about are A, B, and C. These are called Unicast addresses, which just means they're meant for one specific device. And here's the really brilliant part. You can tell which class an address belongs to just by looking at that very first number. If it starts with anything from 1 to 127, it's a Class A, built for a few gigantic networks. 128 to 191, that's Class B, perfect for a big university. And 192 to 223 is Class C, designed for small networks like a small business or, you guessed it, your home.
So what about the other 2?
Well, classes D and E are the special cases. Class D is set aside for something called Multicast, which is kind of like a radio broadcast that only goes to specific subscribers. And Class E is reserved for experiments and research, so you're not going to see these assigned to your phone or your gaming console.
Okay, now we are getting to what is, without a doubt, one of the most important concepts in IPv4. See, an IP address isn't just a single address. It's actually 2 different addresses rolled into one.
It's just like your mailing address. Part of the IP address is like your zip code. It tells you the general neighborhood, or the network. The other part is like your specific street and house number. It pinpoints the exact device, or the host, in that neighborhood. You absolutely need both to get the mail delivered to the right place. So that leads to a pretty obvious question, right? If an IP address has 2 parts, how does a computer know where the network part ends and the host part begins? Well, that is the entire job of something called the subnet mask.
It's another 32-bit number, and its only purpose in life is to draw a line in the sand and tell the computer, hey, this chunk is the network and the rest is the host.
Let's see how this works. For a Class A address, the standard subnet mask is 255.0.0.0. This mask tells the computer to only pay attention to the very first octet for the network ID. That leaves the other 3 octets completely free for host devices. And that allows for, wait for it, over 16 million devices on that one single network. It's massive. Now, with a Class B address, the mask 255.255.0.0.0 draws the line right down the middle. The first 2 numbers are for the network, and the last 2 are for the hosts. This gives you a nice balance. You can have a lot of different networks, and each of those networks can still have about 65,000 devices. And finally, we get to the most common one, Class C. Its mask is 255.255.255.0. This uses the first 3 octets to identify the network, leaving only that final single octet for the host devices. This gives you up to 254 possible hosts, which is just about perfect for most small office or home networks.
All right, we've covered the basics of the public addresses you see out on the internet. But not all IPs are designed to be world travelers. There are special blocks of addresses that are reserved for specific jobs, and they're not allowed on the public internet. You've got 3 main types. There are private addresses, which are used inside your own little local network bubble. There's the loopback address, which is basically a device talking to itself to run a self-test. And then there's something called APIPA, which is a clever backup plan your computer uses to give itself an address if it can't find a router.
But let's focus on those private addresses for a second, because this is a really clever trick. This is why your computer can have the exact same IP address as your neighbor's computer. These addresses can't be routed on the public internet, so they can be reused over and over again in millions of private networks. It's a key reason we haven't run out of IPv4 addresses sooner. And that 192.168 range, that's almost certainly what your home Wi-Fi router is using to assign addresses to your devices right now.
So all these tricks bring us back to our big number, 4.3 billion. That is the hard mathematical limit of IPv4 addresses. But if you look around today, the estimated number of internet-connected devices is over 20 billion. We're talking phones, laptops, smart TVs, cars. The list goes on. We've got a serious math problem on our hands.
And that leads us to the final critical question. We've used all these clever hacks and workarounds to stretch IPv4 as far as it can possibly go, but the numbers just don't lie. In a world with way more devices than addresses, how does the internet keep growing? Where could we possibly go from here? Something to think about. Thanks so much for joining me for this breakdown, and as always, stay curious.